Yeah. Isatomo, if you can admit people while I do this, but hello everybody and welcome to the third joint Hokkaido University Arctic Research Center, University of Alaska International Arctic Research Center joint seminar. Just a couple of overviews. Everybody should be muted upon entry into the room. Please feel free to enter any questions for the speakers that you have into the chat box as we go along, and there will be portions of time where we'll allow folks to unmute themselves and ask questions to the speakers. If you're calling in by phone, I don't think we have anybody right now, but in case you were, please make sure that your phone is muted, which you can do with *6 or the mute button on your phone. Yeah, that's just about all. If you have any questions, you can direct message me, but I'm going to let Hisatomo Waga take it away.
Thank you, Mike, for great introduction. And then I'm Hisatomo Waga, postdoc, working at the International Arctic Research Center at University of Alaska Fairbanks. And today we have two talks, both talking about physical oceanography in the Arctic Ocean with a particular focus on mooring observation. And I'd like to invite first speaker, Andrey Pnyushkov. So Andrey, if you're ready, please start screen sharing and then go ahead.
Okay, so do you see it?
Yes, perfect.
Okay, sounds great. Good afternoon, everyone, and thank you very much for the possibility to speak at this seminar. Today, I will talk about the regime of volume and heat transport in the Eastern Arctic Ocean based on instrumental observation at our moorings. And this study summarizes observational efforts of the international team of researchers, mostly physical oceanographers, led by the University of Alaska Fairbanks, and conducted under umbrella of the Nansen and Amundsen Basin Observational System, or NABOS. Over the recent 7 years, this program was funded by the National Science Foundation grants, and here I would like to present some result of this program. Okay, let me talk a little bit about the motivation of this study and introduce some basic statements related to the concept of Atlantification of the Arctic Ocean. We all know that in a recent decade, the Arctic has experienced strong changes in all components of the climate system. In the Eastern Eurasian Basin, those changes can be attributed or linked to anomalous inflow from the subarctic seas, the processes that we usually call Atlantification, the inflow of Atlantic water into the Arctic Ocean. Originally, the term Atlantification came from biological oceanography and means penetration of biological organisms from the Atlantic Ocean to the Barents Sea. However, in later, this term was used to describe changes in physical component of the system, and in general, now it means that physical conditions in the Arctic Ocean interior or in the deep part of the Arctic Ocean become more and more similar to that condition previously observed in the Atlantic sector of the Arctic. For the Eastern Arctic Ocean, it specifically means that Atlantification increases penetration of Atlantic water signature into the Arctic Ocean interior. It also increases observed as a reduction of sea ice cover, the greater surface heat and moisture fluxes to the atmosphere, the increased depth of penetrative convection, and the increased seasonality in sea ice cover in the state of the upper ocean. Today, I will focus mostly on the first element of this concept, and more specifically on the estimates of heat and water transport associated with the Atlantic water. Why this transport are important for the Arctic, and why we are focused on this? The main reason is very simple. It's because the Atlantic water carries just a huge amount of heat, which may impact the thermal state of the upper ocean and sea ice. However, as we know, this heat cannot be easily released to the upper ocean and to the bottom of sea ice because it's separated by the layer of strong density stratification, which we usually call the pycnocline layer or the halocline layer. However, several recent studies, including several studies which based on neighbors' observation, demonstrated that in recent years, the heat of the Atlantic water can penetrate to the halocline layer and even to the upper mixed layer, and thus affect the sea ice cover of the Eurasian basin. This is why quantification or quantitative estimate of Atlantic water heat transport and Atlantic water heat becomes more and more important in modern condition in the Arctic. To estimate transport, we used observations, we used measurements collected by NEIGHBORS project at 5 moorings deployed at the continental slope of the Laptev Sea in the eastern part of the Eurasian basin. The location of those moorings is shown on the right map here by red circles, where red arrows indicate schematic Atlantic water circulation in the Arctic. We see that Atlantic water penetrates into the Arctic through Fram Strait and propagates along the continental slope in a cyclonic sense, which is here. And our neighbors' moorings cover the depth range from approximately 250 meter depths. This is the shallowest mooring M11 to approximately 3,500 meter depths at the deepest moorings, mooring M15. Here in our study, we used 2 periods of mooring deployment. The first one was from September 2013 through September 2015. In 2015, all these moorings were successfully recovered and redeployed at the same location again. So the second period was from September 2015 through September 2018. So for our analysis, we have approximately 5 years of mooring observation at this section. So the left panels on this slide show the instruments that we used at our moorings. We had 2 types of moorings there. The first one was equipped with McLean moorings profiler, which is a yellow instrument here. And this instrument goes up and down along the mooring line every second day and measure temperature, salinity, and horizontal component of velocities. And the second type of moorings was equipped with acoustic Doppler current profilers. And we also complement these current observations with temperature and salinity measurements made with seabird microcats, which allow us to estimate heat fluxes. And this is two schematic of instruments deployed at moorings in 2013 and 15, and the second deployment from 2015 to 2018. So we started our analysis with evaluation of the crow slope structure of eastward velocity. On the top left panel with eastward velocity, we see a gradual decrease of velocity across the slope from approximately 15 centimeters per second at the shallowest mooring M1 to the negative or westward velocities in the deepest part of the section at mooring N1-5. So to get a more detailed picture of currents, we split the water column for several natural layers, specifically for the upper layer from 10 to 40 meter depths, for the halocline layer from 70 to 140 meters, and for the Atlantic water, which we identify as a layer with positive potential water temperature. So we estimated the mean currents for all those layers, and we found that for all moorings except the most deepest mooring M1-5, the mean current in the halocline layer and in the Atlantic water layer were strongly coherent and follow the same direction generally along the isobot. So you can see on this slide from the bottom panels. We also found that the vector correlation between daily currents in the Atlantic water and halocline layers were relatively high, and they vary from 0.6 at the deepest mooring M1-5 to 0.86 at the mooring M1-4. This high coherence and high vector correlation of the flow in the halocline and Atlantic water layers is likely due to conservation of the potential vorticity, in which the bottom topography plays the major or at least important role. So further, we estimated heat and water transport across the mooring line for different layers. We use the same layers as at previous slide. And this slide shows the time series of monthly transport for all those layers. And unfortunately, we have only 5 years of observations here, and the relatively short record does not allow us to talk about trends. But we split our records for 2 periods of mooring deployment, and then we can attest more or less reliable the long-term variability in our transport series. The mean for those 2 periods, I mean 2013, 2015, and from 2015 through 2018 are shown by dashed lines on all these panels. So what interesting we found here, we found that Atlantic water volume and heat transport have no significant shift in 2013 through 2018. This probably suggests a quite steady regime of Atlantic water advection into the Arctic Ocean. The only statistically significant changes that we found was in the halocline layer, where the water transport reduced approximately by 19%. This probably means that the weakening of Eurasian Basin halocline or Eurasian Basin halocline stratification in recent years, which is also part of Atlantification process, happens due to advection of saltier water from the upstream location, likely from the northern part of the Barents Sea, and not directly connected to the stronger water transport from the Atlantic Ocean. So another interesting feature that we see here is a small increase in the Atlantic water transport, which means more heat that is available for further redistribution in the Arctic Ocean interior. And this increase is about 10%, is evident both in heat transport in the Atlantic water layer and in heat transport density, which is the ratio of heat transport and volume transport. Okay, this slide just summarizes our estimate of transport for different layers and periods. So it, for example, it's useful if we are going to compare our result based on direct observation with some modeling. And what is interesting here is, what I should emphasize here is that our transport have very strong year-to-year variability. So the annual mean transport may vary by approximately 80%. For example, it varies from 2.3 sphere group in 2014-2015 and to 4.2 sphere group in 2016 and 17. So approximately the same level of variability was found for heat transport, because it's very strongly related to the variability of currents across the moving line. So neighbors actually has a very long history of observation in the Eurasian basin. The first mooring under this program was deployed in 2002, and with all this huge amount of data in hand, we tried to reconstruct the net Atlantic water transport back in time, and we did it for 9 years until 2003. And for this reconstruction, we used a linear regression with observation from M1 mooring, which is yellow circle on this map. So this approach, I mean, the linear reconstruction, is based on the fact that currents at the deeper part of the slope at moorings M15 or M1. Moorings M15 and M14, the same as mooring M1. So significantly contribute approximately up to 60% to the variability of the long slope transport across this section. So the reconstructed Atlantic water volume transport, which is shown by dashed blue line on this slide here, shows very strong or substantial interannual variability. For example, Atlantic water transport peaked in 2004-2005 and exceed 8 sphere group. However, similar to what we found for our shorter record, over the entire length of records, approximately 15 years, the Atlantic water volume transport shows no significant trend, which we estimated as minus 0.02 sphere group per year. So we also complement our analysis of mooring-based transport with estimate of barotropic transport for the same segment of the slope. And this transport were calculated with a data set of Arctic dynamic ocean topography And this satellite product allows us to estimate the barotropic Atlantic water transport using a geostrophic relationship. The green line on this slide at the left panel shows a series of the barotropic Atlantic water transport estimated from this data set. We found a very weak positive trend of approximately 0.08 SVERD per year since 2003. But we also found that this trend is almost at the edge of the 95% confidence interval. So it should be considered with very caution, because it may change if we additionally add some observation to these estimates. Okay, so we compared our estimate at the Laptev Sea slope with estimate of transport made at the entrance of the Atlantic water into the Arctic in Frame Strait. We found very close match between the Atlantic water volume transport in Frame Strait and at the Laptev Sea slope. We have about 3.0 SVERD group of the Atlantic water transport in Frame Strait and 3.1 SVERD group of Atlantic water transport at the Laptev Sea slope. Small difference in those transport makes possible a comparison of the Atlantic water heat transport and neglect the uncertainties due to unclosed mass balance. So in Frame Strait, according to the paper by Bishanska-Moller published in 2012, we have about 58.8 terawatt of heat transport, and our estimates at the central Laptev Sea give us about 33.4 terawatt of heat transport, which means that the Atlantic water loses about 25 terawatt on its way from the Frame Strait to the Laptev Sea. So we can speculate about the fate of these heat losses, but we need to understand that not all this heat goes upward, and most of the heat is distributed laterally by heating the surrounding cold waters. So this serves as a major source of uncertainty for the estimate of heat transport based on the difference of heat transport between these two sections. So, however, according to estimates made by Polakov et al., only 7% of this heat distributed upward, which give us approximately the average estimated vertical heat fluxes of 3 to 4 watt per square meter. Actually, these numbers are quite high, because if you know, every 1 watt per square meter is equivalent to the melting of 10 centimeters of ice in annual cycle. So, for example, to explain the recent changes of sea ice observed in the Arctic Ocean over the last several decades, we need to operate the additional heat surplus of just 1 watt per square meter. And here we have from 3 to 4 watt per square meters. So our estimate of vertical heat fluxes agree well with the estimate of vertical fluxes made from the seasonal changes of heat content made by neighbors moorings. According to at least 2 papers published by Polakov et al. In 2017 and in 2020, the winter mean vertical heat fluxes were from 7 to 12 watt per square meters, but this is just a winter mean, so which gives us the estimate of annual heat fluxes from 4 to 6 watt per meter squared, which is very close to what we have from our observation of heat transport, the losses of heat transport. So our estimate is also close to the estimate made from the analysis of double diffusive heat fluxes, which give us from 3 to 4 watt per square meter, derived from microstructure observations from 2007 and 2008. And also agree well with estimate made in a recent paper by Schulz et al., published in 2021. Okay, so we came to the conclusion. So based on our instrumental records, we see no significant temporal shift at annual at longer time scale in 2013 and 2018. The reconstructed volume transport over a longer period of time showed very strong interannual variation, but lacked statistically significant trend despite of weak positive trend in the barotropic Atlantic water transport. So this steady regime of volume and heat transport suggests that that third weakening of Eurasian basin halocline in the 2010s is likely due to saltier water advection from the northern Barents Sea and not related to the stronger influx of water from the upstream location for Fram Strait and from the northern part of the Atlantic Ocean. And the weakening of Eurasian basin halocline is one of the most important signatures of Atlantification of the Arctic Ocean. So we also found very strong and very nice vertical coherence of 2013-2018 transport in the halocline layer and Atlantic water layer, which suggests the essential role of barotropic forcing in constraining along flow transport. So the more detailed explanation of what we really found using our observation can be found in this paper, which is recently published in Journal of Frontiers in Marine Science just a couple of weeks ago. Okay, thank you for your attention.
Thank you, Andrey, for your great talk. So if you have a question, please speak aloud or please type them onto the chat box. I don't see any question on the chat box. So if you have a question, please speak aloud. You can unmute now.
Yeah, I have a question, Andrey.
Go ahead, Mike. Yes.
What about the total heat flux going out of the Arctic? In the Fram Strait area, are the measurements also taking into account heat leaving? Has anybody got that? So to work out a total accounting system.
Could you speak more loudly? So I'm sorry, Michael.
Sorry, it's about accounting for the heat. We've measured, well, someone's measured the heat going into the Arctic at the Fram Strait.
Yes.
You and Igor have estimated heat going upwards. And then the question is, where does the rest of the heat go? You suggested lateral mixing into the rest of the ocean. How do you separate that from heat actually flowing back out of the Arctic, back into the Atlantic?
Actually, in our estimate, we just utilize the ratio of heat which goes upward from the paper by Igor Polakov. So you're absolutely right, and the part of this heat is transported back to the Atlantic Ocean with outflow of Atlantic water in the western part of the Infram Strait. And part of this heat is distributed upward and goes to the atmosphere, it's not related to the melting of sea ice. And some portion of this heat is also distributed laterally and goes to heat the colder Barents Sea inflow, the Barents Sea branch of Atlantic water, and also goes to the heat of shelf water and dense shelf water due to cascading processes. So we cannot estimate with our observation in hand how much heat is transported back to the Atlantic water, to the Atlantic Ocean in Infram Strait. So we just can make this estimate based on the divergence of heat fluxes in Infram Strait and at the Laptev Sea.
Thank you, Andrei. That helped me a lot. Thanks.
Okay, Jika-san, go ahead.
Yeah, thanks. Thank you, Andrei, for this interesting talk. As a non-oceanographer, may I ask you a question? So as I understand, for heat and volume transport, since 2003 till 2018, there is no significant evidence for change. How about modelers trying to see the trend? Are they surprised by your result? How do you feel? Did they expect a different picture? Did they expect it would be possible to detect? Could you elaborate a bit about what modelers were expecting and what your data tells?
Yeah, actually, it's a very nice question. And we try to compare our result with several models and several available reanalysis models. And right now we see a very big difference of what we have from the point of view of observational oceanography and what the model can reproduce. Because for some reason, the Arctic Ocean models not always good in reproducing the inflow of Atlantic water, and especially in reproducing the propagation of Atlantic water, how it changed on the way from Strait to the central Laptev Sea. So we see just a huge difference of how the model reproduces the thermal state of the Atlantic water. So I cannot believe without very big progress in the modeling that the model can reproduce the trend in Atlantic water volume transport and the heat transport without any increase of, let's say, resolution of models or some processes that need to be more described in more details. So right now we have very large difference of what we have from the point of modeling and from the point of observations.
Fascinating. Thank you very much.
Any question? All right, so let's move on to the next talks. Thank you, Andrei. So next speaker is Miyaki Muramatsu, who is a PhD student at JAMSTEC as well as Hokkaido University. So if you are ready, please go ahead and please start share screen, Miyaki.
Okay. Okay, can you see my slide?
Yes, perfect.
Okay. Hello everyone, I'm Miyaki Muramatsu. I'm a graduate student of Hokkaido University. Thank you for giving me the opportunity to introduce our study. I'm studying the heat transport in the Arctic Ocean. Today, I'd like to talk about the Pacific summer water transport in the Arctic Chukchi Northern Slope. First, sea ice reduction in the Arctic Ocean has intensified over past decades. This figure shows the sea ice extent on September 1st in last year. September 1st in last year. The white area in the center is sea ice extent, and these white bold lines indicate the sea ice age in 1980s. The sea ice age in last year was located further north of sea ice age in 1980s. This year's reduction, especially in the Pacific side. Pacific side is associated with the Pacific summer water inflow in Bering Strait by previous studies. This figure shows the Pacific summer water transport in Chak Sea. The Pacific summer water flow into the Arctic Ocean through Bering Strait here. The temperature of the Pacific summer water is greater than 0 degrees Celsius. According to the previous studies, Bering Strait transport has been increasing in these decades. After passing through Bering Strait, most of the Pacific summer water reaches Barrow Canyon in the northeastern Chak Sea and flowing to Canada Basin. Recently, previous studies indicated the west current in this region. This shows northeastern Chak Sea. Here is Barrow Canyon. Quest and Pickett 2017 suggested the presence of the westward current. The current flows along the Chak Sea northern slope from Barrow Canyon and is called the Chak Slope current. The current transports the Pacific summer water northwestward. We et al. 2019 clarified the seasonal characteristics of the Chak Slope current. However, detailed characteristics of the Pacific summer water transport by this current remains unknown. So we analyzed the data from mooring observation along the Chak Slope current in 2003 to 2005 and 2015 to 2019. Sorry, this is 2019. In our study, we clarify the advection time and temperature change of the Pacific summer water in the Chak Sea northern slope. We use temperature and salinity and velocity data obtained from mooring observation at station HSN and HC in the Chak Sea northern slope. The moorings were deployed at station HSN here from August 2003 to October 2005, and at the station NHC here from September 2015 to 2019. We also used the mooring data obtained in Barrow Canyon. In addition, we used the following two datasets. The SIPON hydrographic data obtained in 1999 to 2019 was used to calculate the ocean heat content and stratification index. The reanalyzed wind data were also used. This is the TS diagram at station HSN in the Chak Sea northern slope. In our study, the water within this red bold line was defined as Pacific summer water. referring to the definition suggested by the previous studies, such as Quart and Pickett 2017 and Rieter 2019. The lowest temperature here, lowest temperature said to be freezing point +1 degrees Celsius. These colored dots represent water properties in each layer. These layers were defined based on the ocean heat content as explained in next slide. This figure shows the vertical profile of ocean heat content ratio. The ratio was calculated using this equation. OHC surface to H indicates the ocean heat content between sea surface and depth H. And OHC surface to 150 indicates H is 150. At the surface, the ratio is 0%, and the value reaches 100% in the depth of 150 meters by this definition. In this study, we defined the layer in the ocean heat content ratio or range of 50 to 70% as layer 1. Layer 2 is defined as layer with ocean heat content ratio 70 to 80%. Layer 3 is 80 to 85%. Layer 4 is 85 to 100%. This orange part with this vertical profile denotes the layer which is the Pacific summer water present in it. So here after we focus on the layer 1 as the Pacific summer water core layer. Here we show the temperature time series recorded at the station HSN and HC in the jagged sea northern slope. The colored section indicates the presence of the Pacific summer water, and we call the section Pacific summer water term. We calculated the average temperature for the Pacific summer water term. In layer 1, the average temperature was 0.0 degrees Celsius in period 1 and 0.3 degrees Celsius in period 2. We also investigated the time series of the velocity in the depth of surface to 100 meters at station HSN and HC. The red part in this figure indicates northwestward flow. And the blue part is southeastward flow. Black rectangles denote the Pacific summer water. The current direction was mostly northwestward in the Pacific summer water core area, both in period 1 and period 2. In the layer, the average velocity of the northwestward current for the Pacific summer water term was 15.4 centimeter per second in period 1 and 20.9 centimeter per second in period 2. The northwestward current suggested that the Pacific summer water at the station HSN and HC came from Barrow Canyon. So temperature time series and the average temperature for the Pacific summer water term at station HSN and HC were compared those in Barrow Canyon. This is the temperature time series at the station BCC in period 1. These orange lines in time series denote the October 1st in 2004. For the colored Pacific summer water term at station HSN and HC, that is after October 1st in 2004, lagged behind the term at station BCC, that is mostly before October 1st in 2004. Then lag correlation analysis was applied between the temperature time series at station HSN and HC and those at station BCW, BCC, BCE to investigate how many days it takes for the Pacific summer water to be transported in the Pacific summer water core layer from Barrow Canyon to station HSN and HC. As a result, the temperature time series at station HSN and HC lagged for 7 to 61 days in the Pacific summer water core layer from Barrow Canyon to station HSN and HC. Here, I'd like to summarize the Pacific summer water transport in the Chakchi briefly. Previous studies indicated the Pacific summer water passed through Bering Strait from May to October, and more of them reaches Barrow Canyon from July to December. In addition to that, our study suggested that it takes 7 to 61 days for the Pacific summer water to be transported in Pacific summer water core area from Barrow Canyon to station NHC. Next, in the Pacific summer water core area, we compared the average temperature for the Pacific summer water term at the station HSN and NHC, and the average temperature at station BCW, BCC, BCE. Delta TPSW, this is the temperature change between the Barrow Canyon stations, that is station BCW, BCC, BCE, and the Chakchi Sea Northern Slope stations, that is station HSN and HC. If the temperature change is positive, show as red, the value indicates the average temperature for the Pacific summer water term increase during the transport from Barrow Canyon to station HSN and HC. On the other hand, if negative, show as blue, the value indicates the average temperature decreased. We found the temperature for the Pacific summer water term mostly decreased during transport from Barrow Canyon to station HSN and HC. And the temperature decrease in period 2 was larger than that in period 1. And in this region, the surface water was fresh and cold. So we hypothesized that the vertical mixing with the surface fresh and cold water could be a potential factor of the temperature decrease. Mixing could be enhanced by a combination of weak stratification, a strong wind, and vertical shear of the velocity. So we investigated the relationship between temperature decrease and the stratification index in the Pacific summer water core layer first. The low stratification indicates weak stratification. The negative value in vertical axis indicates the temperature decrease from volcano to station HSN and NHC. The stratification index was low in 2016 and 2017. That is in period 2. The stratification was weak in period 2 when temperature decrease was large. We also investigate the relationship between temperature decrease and the average wind speed, but local wind did not account for temperature change. Furthermore, we calculated the vertical shear from the mooring velocity data as an index for the vertical mixing. Vertical shear was large in period 2. This strong vertical shear in period 2 supported the strong vertical mixing with surface water in this period. The strong vertical mixing with surface fresh and cold water in period 2 was consistent with the large temperature decrease in period 2. Summary, in this study, we found the Pacific summer water at station HSN and HC came from Barrow Canyon, and it took 7 to 61 days for the Pacific summer water to be transported in the Pacific summer water core layer from Barrow Canyon to station HSN and HC. And in period 2, temperature decrease was larger than that in period 1 because of enhanced vertical mixing. However, the Pacific summer water transport to Canada Basin is not understood. So we are now trying to understand the Pacific summer water transport and the heat flux in the downstream region using SIPCON data. The paper including to this content is available as an article in press in Polar Science. I'll be glad if you visit our article. Thank you for listening to my presentation.
Okay, thank you, Miyaki, for your talk. Any question for Miyaki? If you have a question, please unmute yourself and speak aloud.
Okay, can I have a question?
Yes, please.
Thank you for interesting talk. And my question is the lag between the two stations from 7 to 61 days is in very large, is a very wide range. What determines the lag or speed of the current between the two stations?
The result, including BCW to HSN and HC and BCE to HSN and BCE to HSN and HC, but the Pacific summer water, which pass through in the eastern of the Barrow Canyon, from eastward along the Alaskan coast and turned westward. So the
Okay, you can share your screen if you want.
okay.
Yeah, I can see your screen.
Okay. Sorry. some of Pacific summer water which pass through volcano flow eastward along the Alaskan coastal current and turn. So the transport route is little different, and so the lag is wide range. Okay.
Right. And have you measured the current speed in those regions?
Measure speed. Speed is about 15 centimeter per second, but the velocity is also the range.
Have
maybe,
a wide range?
Yes. Maybe the velocity exceeds 30 centimeter per second.
Okay, and time estimated from that velocity is matched to the time now of the 7 to 61 days from your mooring data.
Yes. Yes, this 40.6 to 39 to 7 centimeter per second. This value is calculated by the distance between the volcano and HSN and HC, and lag and this lag. But this value is in the same order as the velocity observed at station HSN and HC. Obtained station HSN and HC. The value station HSN and HC is obtained is calculated from the mooring data. Okay.
Okay, thank you.
Okay, thank you. And any other question?
Yaki,
Yes.
this could be a very dumb question, I'm sorry.
Yes.
But between two moorings, you measure the water properties at the first mooring, and then you measure the water properties at the second mooring, and you looked at, for example, temperature changes. How could you tell that you're measuring the same water stream? Is there some tracing property, or is there an assumption that the water stream does go from or go through both those moorings?
Yes. I think this region is strong salinity stratification, so the same layer is same stream, I think.
Okay, so you are using salinity as some kind of confirmation that you're staying in the same stream from mooring 1 to mooring 2?
Yes.
Okay, thank you.
Yeah, thank you, Michael. So any other question? Okay, so it's almost 5 p.m. or 10 a.m. So I'm gonna close this seminar today. So thank you, Andrey, for Miyaki, for your great presentation today. And then our next seminar will be in October. Yes, in October. So I'm really happy to be here to hold this seminar again in October. So thank you so much for coming today. And then, yes, it was great to see you and have a good day.